Have you ever stopped and wondered how a computer solves a problem that has more possible answers than there are atoms in the entire universe? Well, today we're going to deconstruct local search. It's this really clever AI strategy that tackles exactly that kind of impossible-sounding challenge. So, let me just ask you this. How would you even begin to find the single best answer to a problem with a nearly infinite number of possibilities? I mean, that's the kind of question that can make even the most powerful supercomputers just completely grind to a halt. Because that's really what we're talking about here. It's this constant search for the best possible solution floating in a huge sea of options. You know, there's a formal name for this. It's called an optimization problem. And it turns out they're absolutely everywhere. And look, we're not just talking about little academic puzzles, even though something like the 8 queens problem on a chessboard is a classic example. No, we're talking about massive, real-world challenges, like designing the incredibly complex circuits inside your phone to get the most speed while using the least amount of power, or figuring out how to structure a global communications network to cut down on delays. These are just colossal tasks.
So how in the world does AI even start to tackle this? Well, instead of trying to look at every single possibility at once, which, is literally impossible, it uses this surprisingly simple and honestly really intuitive approach. It just tries to find a solution that's one tiny step better than the one it already has.
This whole strategy is called local search. And what's so interesting about it is its philosophy. See, unlike a lot of other algorithms that map out this meticulous path from start to finish, local search, it doesn't care about the journey at all. It's kind of like being dropped in the middle of a giant maze. Instead of going back to the entrance to solve it, you just focus on making your current spot a little bit better. So here's the absolute key idea. You start with just one possible solution. Any random solution will do. Then you look at its immediate neighbors. You know, the solutions that are just one small change away. And if you find a neighbor that's even slightly better, you move there. That's it. That's the whole loop. Simple, right? And that simplicity, that's its superpower. Because you're only ever keeping track of your current position, it uses almost no memory. And that makes it perfect for sifting through unbelievably massive or even infinite sets of possibilities. It's fantastic at finding good, solid, reasonable solutions, especially in cases where finding the one perfect solution is just computationally impossible. All right, so to really see how this works, let's look at the most famous and probably the most straightforward type of local search. It's called hill climbing, and honestly, the name gives you a perfect mental picture of exactly what it's doing. So I want you to imagine that every single possible solution to our problem exists somewhere on this vast, rolling landscape. The goodness of any solution is just its altitude. So bad solutions are way down in the valleys, and the absolute perfect optimal solution, that's the highest peak on the entire map. We call that the global maximum. The hill climbing algorithm does, well, exactly what the name says. It's just a simple loop that constantly takes steps in the direction of increasing value. So in our landscape metaphor, it only ever takes a step that goes uphill. It's a pretty greedy approach, right? It always chooses the immediate, most obvious improvement it can find. Let's break it down. Imagine you just parachuting in and land at some random spot on this landscape. You look around at all the places you could step to right next to you. You find the first one that's higher than where you're standing, and boom, you move there. Then you just do it again and again and again, always moving uphill, until you get to a point where every single spot around you is downhill. Okay, so at that point, the algorithm stops. It thinks, hey, I've reached a peak. But this is where we see the central flaw, the big weakness in this simple strategy, because there's a trap lurking in that landscape. Just think about it for a second. What happens if you climb all the way to the top of the hill, you look around, and every direction is down, but you can clearly see a much, much taller mountain way off in the distance? Well, you're stuck. And this visual illustrates the problem perfectly. The algorithm can't tell the difference between a small foothill, what we call a local maximum, and the true highest peak, the global maximum. Because it's so greedy and will never take a downhill step, it just finds the nearest peak and declares victory, even if a way better solution exists somewhere else. So here's the key takeaway. From the very top of that local maximum, every single possible move is a step down. And according to the algorithm's simple rules, that means there are no more improvements to be made. So it just stops. It gets trapped, completely satisfied with its good enough, but definitely not perfect solution.
Now, this is obviously a big problem, but of course, computer scientists have developed much smarter ways to search, really clever variations of this idea that know how to escape these kinds of local traps. So let's check a few of them out.
So if our basic hill climbing algorithm is like a simple climber who gets stuck pretty easily, we can think of other algorithms as being way more advanced. You've got simulated annealing, which is like a smarter climber who knows that sometimes you have to go down a bit to eventually get higher. And then you have genetic algorithms. That's like deploying a whole team of climbers all over the map at once, and they all share notes about the best paths they're finding. Let's just focus on simulated annealing for a second. The genius move here is that it allows the climber to occasionally take a bad step, to move downhill on purpose. And that little bit of randomness is just enough to let it escape those local maximum traps, cross the valleys, and explore other parts of the landscape, hopefully finding its way to the true highest peak. You know, the idea of local search is just so powerful because it's so simple. Don't try to solve the entire massive problem all at once. Just start somewhere and find a way to make it one step better. So I'll just leave you with this question. Where could that simple, one step better approach help you solve a complex problem in your own life? Thanks for watching.